Every normal distribution we see effectively looks the same. They all look like this bell curve. The only thing that differentiates one from another is what the average is and what the size of the standard deviation is. So I could quite literally use this curve to represent any normally distributed continuous variable. All I need to know is what the average is and what the standard deviation is. So sometimes, and our textbook will use this abbreviation, you'll just tell me what the mean is and what the standard deviation is, mu and sigma, and we'll go from there and say, here's our curve and mu sigma. As long as we have a central mode, symmetric data with tapering tails, I can use this sort of distribution for our behavior. As a matter of fact, we'll develop tools to determine whether or not a population is normal without having to do the whole survey, a census, but we'll use this for a lot of future purposes. Things that are normal. I go to a bottle filling station and I say, okay, you're filling 2-liter bottles of Pepsi. How much is actually in each bottle? You're filling makeup containers, lotion. It says 4 ounces. Is 4 ounces actually in here? I go to a cement factory, 50-pound bag of Quikrete. Does it actually weigh 50 pounds? Some bags are a little high, some bags are a little low. But overall, the distribution of the weights of the bags tends to look like that, with a mean of 50 pounds. And then whatever variation is the tolerance of the equipment. On page 239, I have 2 different distributions. The diameter of a golf ball, mean is 42.7 millimeters, and the standard deviation is 1/100th of a millimeter. This is scores on the CPA exam with a mean of 70 and a standard deviation of 10. It's the same picture. The only difference is the labeling. So I believe it's to my benefit to strip those numbers away and actually not use the mean and the standard deviation. Let's consider this normal distribution. A normal distribution whose mean is 0 and whose standard deviation is 1. Best part. I know exactly what this curve looks like. Looks just like that, but those horizontal marks on the x-axis would just be 1, 2, and 3 to the right, -1, -2, -3 to the left, 0 right in the middle. This is called the standard normal curve. Wait a minute, wait a minute. Standard. We previously talked about taking all of our data and standardizing it. What did we mean when we said we were going to standardize our data? The z-score. So really, this distribution is a distribution of z-scores. So here's a sneaky idea. Instead of dealing with any distribution, let's take whatever data we've got and turn it into the z-scores, and then use this standard normal distribution instead. Now, page 241 shows me the standard normal distribution, the PDF, and the CDF. But that's the same picture. Notice the only change is to the labels on the x-axis. And this is the cumulative area from all the way on the left up to whatever point we're at. So when we get to 0, that area is half the curve, because that's 50%. Symmetric, right? So now, instead of thinking about trying to do a normal distribution with an arbitrary mean, an arbitrary standard deviation, if I say, no, I'm going to switch to the z-scores, then I can do that one instead. This means probabilities now become finding areas under this one curve. And it turns out that we can actually write the PDF formula for this. But if you remember, the formula had the 1 over the square root and the e to the, oh, no, I don't want to deal with that. Disgusting. I don't want to do that. And finding the area under the curve is a calculus problem. Advantage number 1, I don't have to do calculus, provided somebody else already did it for me, or I have my technology in front of me. So what I can do instead is the same thing we did with the binomials. With binomials, we had a table. I get exactly that same table in 2 different ways in the appendices. Table C in the appendices, C1 and C2. The table C1 is normal areas. Now notice the area they are giving me. In the upper right corner here, I have a picture. And this table shows the normal area between 0 and Z. We're getting this part right here. So if I give you a z-score, say 0.25, then you can go 0.25, and you'd be able to say, oh, if I went from 0 to 0.25, the area would be 9.87%. I can use this table directly. I don't have to do the calculus to find the areas. I do need to know what area I'm looking for, but all I have to do is use this. I'm used to using table C1, but table C2, that says cumulative. What this table does is it gives me all the area less than whatever z-score we pick. So this is the cumulative one, starts all the way to the left and just goes up to our z-score. I'm used to using table C1 more than table C2, but I've got them both. Let's do some examples and see how the hell this thing works. I think the most important thing you can do to try and work on these problems is to draw pictures. Even crappy pictures help. So here, we see at the top several examples of pictures we could use, but I'm going to do problem 15 here. Problem 15 says find the area and explain why. I want to know the chance that my z-score, notice we're not using the probability of x anymore. They explicitly write z. What's the chance z is between 0 and 0.5? Well, I'm starting in the middle. I'm going to use table 1, since that's the one that starts in the middle, based on this little picture up in the corner. So I say to myself, oh, I need to go to 0.5. 0.1, 2, 3, 4, 0.5, 0. So the answer to this is 0.1915.
Well, that was easy.
Like that. Well, what happens when things start to get more complicated? Part B of this problem asks for this. The first thing I notice is that in this table, there are no negative z values in table C1. All of the z values over here are positive. So how can I figure out what's going on when z is negative? Max?
The negative value of it? No.
Probabilities can never be negative, right? A probability always has to be a positive number. Right?
It's like the same on both sides.
It's the mirror image, right? We're on the left half instead of the right half, but the picture is symmetric. I can exploit that symmetry. A value of negative 0.5 would be the exact mirror image of what happened over here where the value is positive 0.5. So this probability, again, a crappy picture helps. My picture should look like that. But that's the same area as if we were on this side. Just flip the picture over. So this area is equal to this, which is exactly 0.1915, just as we got before. A note. This is a continuous random variable. The chance of getting exactly a number is 0. So the chance of getting exactly 0.5 is also 0, right? So here's an interesting note. This 0.1915 is also the same chance whether I have equal signs on those numbers or not. Because you can't exactly land on the edge. The chance of getting right on the edge is not going to happen. So whether you have the equal signs or not, in a continuous variable, doesn't change things. All of this is based on this picture. So I'm going to keep drawing these crappy versions of this picture so I can figure out what area I'm after. Questions? First thing I want to do, draw the picture. Draw your normal distribution and put the Z marks where we think they go. So negative 1.22 is over here on the left, and 2.15 is over here on the right, and I want all of this area. Hang on a second. I'm going to actually do this in 2 steps. This would come off of table C1, wouldn't it? This would also come off of table C1. So let's split this in half. You're either in the area on the left or you're in the area on the right. Wait a minute, I used the word or. Back to that counting stuff. How do you do ors? What math operation goes with or? Add. And they're disjoint, right? You're either on the left, on the right. You can't be both. So you take the chance to the left, chance to the right, you add them together. So I'm actually going to write out all the little details here. I'm going to say, oh, this is really the probability of negative 1.22 less than z less than 0, or probability of 0 less than or equal to z less than 2.15. And now I can go to table C1 and I can say, wait a minute, negative numbers aren't on table C1. That's the same as 0 less than z less than 1.22. I just flipped the picture over. So really, I can use table C1 twice. 1.22, 1.2, 1.20, 1.20, 1.21, 1.22, 0.3888. What's this one? Appendix C. Grab your book, open it up to the way back. Aha. 2.101234.5. 0.4842. Add those numbers together and we get so there's an 87.3% chance that your z value is between negative 1.22 and 2.15. I'm jumping around between the problems in the section. Let's think about this one. The chance that z is bigger than 1.28. Now, there are 2 different ways to do this problem. First thing I'm going to do, either way, is draw my picture. $1.28 is over on the right somewhere. And I want the chance that we are bigger than 1.28. That's this piece. So now I say to myself, I have a problem. None of my tables show me that piece. Table 1 shows me this piece. And table 2 shows me this piece to the left of my number. This is to the right of my number. So you can use either of these tables to get the answer. We just have to do a little work to get there from here. Michael, so you're flipping. Which table were you looking at?
Second one.
Okay, the second one gives me the stuff to the left of my number. Yes? That would give me all of this unshaded area. So if I use table C2, then that's all the stuff that is currently unshaded. And Mike, you got that number for me somewhere? But that's the stuff that's unshaded. I want the stuff that's shaded. How do I get there from here?
Okay, when you got this is one.
Because the probability under the whole curve must be 100%. So it's 100% minus this. Which is 0.1003. Now that's method one, using the second table. But I could also use the first table. If I use table one, then I get this because table C1 starts in the middle. Yes? It starts, put the table in the wrong place. It starts here at 0. So what's this number based off our table? Off table C1. But since table C1 only gives from the middle over, it's really only looking at half the picture. So this number is the unshaded area here. How much area is under that whole side of the graph? 0.5, because that's half the picture. And lo and behold, I get exactly the same answer. So really, regardless of whether you use table 1 or table 2, you can get the same answer, provided you know what picture represents the thing you're looking for. Whether you're looking for a tail, an area that is bounded on both sides, or an area bounded between 0 and something, I can use whichever table I want. Questions? To me, the biggest piece of what we do here is drawing that picture. Because once I have the picture, I know what I'm looking for. I can go to the table and figure out how to get it. But notice I'm remembering the rules we did for probability. Whenever I see the word or, I'm going to add. If I see the word and, I'm going to multiply. Whenever I look at the whole graph has to be 100%. So it's 1 minus to get the opposite of. I can also go the other way. If I know a z-score, I can figure out what x gives it to me. Let me go back to the example that was doing uniform CPA exam grades. So if I look at the CPA exam in the book, it says that the CPA exam had an average of 70 and a standard deviation of 10. And I say to myself, I would like to know what the top 5% is. Well, wait a minute. I'm not even dealing with area yet. Top 5%. Oh, wait a minute. No, that is an area, isn't it? I want to know what number gives me the top 5%. Oh, okay. So I go over to my table, either C1 or C2, your call. Which one do you want to use? Table C1 or C2? Okay, if I'm going to use C1, I'm looking for that. But if I'm using table C1, Harry, then what is table C1 gives me the area from 0 to thing, right? So I would need to know this unshaded area. What is the value of that unshaded area? Because the total on this side is 50%. So I can use table C1 to find the area that is 0.45, or at least the closest thing we've got to it. So I grab my table and I start looking. 0.437, 48, 449. Oh, look there, right there. I've got two numbers. I've got 0.4495 and I've got 0.4505. So 0.45 is right in the middle between those. So right in the middle between these, 1.6 between 0.4 and 0.5. So 1.645. Split the difference right in the middle. And I get 0.1645. Now you can tell me what's the score on the CPA exam that is a top 5% score, because that's actually the question I asked. What score did this person get to be in the top 5%? Oh, we said that the average was 70 and the standard deviation was 10. I have the z-score, I can figure out the x score. Put in all the numbers I know. So if your grade is an 86.45 or higher on the CPA exam, you were in the top 5% that year. It turns out there are some numbers we use a lot for benchmarks like this. Questions? Page 245, table 7.7. Please notice, they've given this to me two different ways. If I go to 1.645, then the right tail is 0.05. But by symmetry, if I go down to negative 1.645, that would be the low end, wouldn't it? So the middle, 5% on the high end, 5% on the low end, the middle is 90%. Page 245. And I'm going to tell you right now, these three numbers right here, these are the ones we're going to use the most often. And realistically, I can do this for any number, even if it's not on my table, because I can do all of this stuff in Excel the same way, because we are using a normal distribution. But what we did here was to work that normal backwards. We inverted it. So, open Excel and share it with you. If I said I wanted to know the inverse normal, I could use all sorts of inverses. Right there at the bottom, I just typed inverse, INV. And right down there at the bottom, it says norm.inverse. So let me write norm.inverse. There's my inverse normal. And it says, give me the chance you're looking for, and then what the mean is and what the standard deviation is. My probability is 5%, right? Oh, wait. I was looking for the top. Hang on a second. I'll show you what happens here. 0 and 1, because I was doing the standard. Why did it give me negative? It's still 1.645, but it gave me the negative one. It's doing the cumulative by default here. So if I want the top 5%, I really want to know what the 95% mark is. There's my z-score. If I give it the 70 and the 10, (0.95), 70 for the average, 10 for the standard deviation, it'll give me the X value back automatically, 86.45. So I can do all of this even if I don't have my table in front of me, as long as I have a piece of software to cover it. Otherwise, I'd have to work the calculus out, and that would just be a nightmare. And I'm going to make you do that. These also work in here. Here's my distributions. The distributions are over this button that says variables. So you hit the second and that brings you to this screen. And I wanted to do the inverse normal. There it is, number 3. Inverse normal. What area do I want? Oh, I wanted the 95% mark. The average was 0. The standard deviation was 1. I hit paste. It pastes that into the area, into the home screen. There's my calculation. I am an old fart. When I learned this, the only thing I had was the table. As soon as we got calculation devices that worked this way, and spreadsheets that you could use in the classroom, I was thrilled to not have to do this by hand all the time. But when I took my stats class, I had like 7 pages of tables in front of me the whole time. Questions? Please notice in our table, in both Appendix C1 and in C2, there's a box in the middle of the page. Right here, in Appendix C1, it's here in Appendix C2, and there's the one that was boxed in Appendix C1. So what's the deal with that? If we look, that's at the number 1.96. According to that table on page 248, 1.96, hey, that was one of the numbers I used all the time. The middle is the 95% section. So that 0.475, that leaves 2.5% on the upper tail and 2.5% in the lower tail. So it's 5% on the outside and 95% on the inside. When you talk about having a confidence, remember we talked about type 1 errors and type 2 errors, whether something was a mistake one way or another. Well, I haven't covered that yet. Stop, rewind, erase that, sorry. When we talked about our significance on our tests, we talk about whether we had a false positive or false negative. That's the piece I've talked about here. How do we determine those numbers? Well, we're using this sort of confidence behavior. And that 95% mark is one we're going to use a lot. Helps if I remember which I've covered in what classes. I apologize. Problem number 27. The fastest 10% of runners who complete the Nosy Neighbor 5K race win a gift certificate to a local running store. Assuming a normal distribution, how many standard deviations below the mean must the runner's time be to win a prize? Okay, wait a second. I'm not asking for their actual time because I don't know the average or the standard deviation yet. But how many standard deviations below the mean? That's a z-score. So I'm actually asking for a z-score here. And I'm asking for the z-score. The fastest are going to have lower numbers. So I want the fastest 10%. In terms of my picture, what I want is that area to be 0.1. The fastest 10%. But I don't know the mean. I don't know the standard deviation. So I put a question mark next to those. But what I do know is that I want the area to be 0.10. Which table do you think will be more helpful? Table 1 or table 2? Just based off this picture, Harry?
Yeah.
Because this is from the left to a number. This is a cumulative question. So I use the CDF. And now I go grab my CDF table, chart 2, and I go and I say, oh, I want the area to be 0.10. And I start looking. Where do I get an area of 0.10? I got to go down the table further because there's 0.02 and I want 0.10. Okay, here we are. I start to see things in the 0.10 range around here. 0.103985 here-ish, right? 0.10 should be between these two. So let's use the little bit smaller one to guarantee it. That is 129. It'd probably be a little bit closer to 128 than 129 because 0.1003 is closer than 0.0985. If I switch to Excel or I grab my calculator, I can get an exact version here. This time, instead of the 95% mark, what I would want is the 10% mark. Hey, 12815. Oh, that's closer to 128 than it is to 129. As long as I convert to z-scores, I don't ever need anything but one distribution. And that makes my life a lot easier. It means I only need one table. I don't need a different table for every mean and every standard deviation. The shape is always the same as long as I use the standard normal. So if I'm asked a question like this one, the volume of liquid soap in a randomly chosen bottle of dish soap is normally distributed with an average of 600 milliliters and a standard deviation of 5 milliliters. Okay. Problem 7, number 29. Problem 7.29. What is the chance that I have more than 592 mils in my bottle? What I need from this is the z-score. So 592, the z is negative 1.6. So my actual chance is what? Draw me a picture. Negative z. And we want the chance of being bigger. Which table do you want to use? Because the cumulative one will give me the stuff to the left. That's the unshaded part. And to get the shaded part, since the total is 1, I take 1 minus this table value from C2. Negative 1.6. It's the value for negative 1.6. 0.0548. 1 minus that. 0.9452. 94.52% of the bottles will be at least 592 mils. I can use this exact idea regardless of the setting. Same idea, problem 31. The number of calories in a McDonald's Egg McMuffin is normally distributed with a mean of 290 and a standard deviation of 14. I know the average and the standard deviation. What's the chance your Egg McMuffin is extra fatty today? And you get one that's more than 310 calories. I personally, I'm not sure I care, but I also don't eat at McDonald's very often. But if you're a nutritionist, isn't this an important statement to you? If you're training for something, there's a whole set of rationales as to when one of these is more or less useful. We'll do a bunch more examples when we get back. So we'll see you all in 10 days. Enjoy the break. See you then.